Good day, everybody, and welcome to the OptiFiber webinar. We thank you for joining. My name is Brian Tipper. I'm the VP of Sales and Marketing at OptiWave, and I'll be sitting alongside your host, Steve Dodds. Before we begin, let me outline a couple things. First off, I'll be launching 3 polls during the course of the webinar, and we greatly appreciate if you guys can answer them all. Also, everybody that's present for all 3 polls will be entered into our $50 gift card draw, in which the winner will be announced in 1 hour from now. We also have 2 question answer periods, the same as previous sessions. The first one's going to be at the halfway mark, so about 20 minutes in, and the second will be at the very end of the webinar session. And finally, the webinar is going to be recorded and distributed to everybody that registered. So if you did register, you're going to receive a link to the video in an email tomorrow around 2 p.m. Eastern Standard Time. So now let me welcome your presenter, our OptiFiber product manager, Steve Dodds.
Thank you, Brian. Thanks for the introduction. And let me show you my screen. Okay, looks good. So welcome to the OptiFiber webinar. OptiFiber is a software which can be of help in the design of optical fibers. In OptiFiber, you provide design of fiber either as a refractive index profile or a dopant profile. And then OptiFiber goes and calculates the optical modes on the fiber and calculates a bunch of other optical properties as well, and I'll be showing all of those today. When OptiFiber starts, you get a blank page, and at this point, it is waiting for you to say something about the fiber that you've got. You need to design the fiber first. Yes, and then Fiber can show you that you can specify a design by either refractive index profile or dopant index distribution. And so I'll show refractive index file. And this is achieved by adding a couple of layers. So this is the axis down here is the radius from the center of the fiber. And the first one is a radius of length 10 with a refractive index of 1.44692. The second layer has the same dimensions, but I'm going to change the refractive index of the next layer to 1.44, so that functions like a cladding layer. You see it's lower than the first layer. These are refractive indices, but because the material of the fiber, glass or some kind of glass, is dispersive, those numbers don't mean anything unless you specify the wavelength at which this refractive index applies, and that's the meaning of the wavelength number we see there. This material is the cladding material, has refractive index 1.444 at an optical wavelength of 1.3 microns. So this is a simple basic step index fiber design. It'll do for our first look at OptiFiber, so we can say OK to that. And this is actually a project file. We can save it. This is Thursday, so I'll call this project Thursday. And it shows a representation of our optical fiber, a core diameter of 10 microns with some cladding on either sides. Having done this, OptiFiber is now able to calculate some optical modes. So it has gone and calculated what modes could be found at the wavelength 1.3. It's calculated LP modes. And here's LP01 looks like that, and 02 like that, 11 is like that, 22 is like that, and so on. A shorter wavelength, of course, you'd end up with more modes. And having calculated the modes, we can do something with them that is sometimes interesting. I'm going to select all of the modes of this fiber, and I'm going to compose them. And in this dialog box, I have a list of the optical fiber modes possible on this fiber. And to each one, there is an amplitude and a phase assigned. It's just arbitrarily set the amplitude of each mode equal to 1, and the phase to 0. And it can show what would happen if you excited this way, all modes with equal amplitude. Well, it would look like this. And that's a kind of a mixture of all of the modes that were found so far. We're able to do something else at this point too, because if this is what the situation was at one point in the fiber, we'd be able to determine what the field will look like at some later point, because knowing the modal index of each mode, it means that if we move ahead by some distance, let's suppose we move ahead by 1,000 microns, so we're going to propagate 1 millimeter farther. What's going to happen is a millimeter from now, all of these modes will still have the same amplitude, but they'll have different phases because their phase accumulates according to the modal index. So after some distance, like a millimeter or so, they'll all be in a different phase. So if it looked like this at this point, a millimeter later, it's going to look like that. And you can get all kinds of funny shapes this way. It gives you some idea of what multi-mode propagation looks like. And we can, this is step index fiber, but we can also do graded index fibers. So I'd like to just demonstrate that too. Just call it a project different name. That in this design, I set the first region, the core region, was said to have a constant index. Doesn't have to be constant. We could set it to one of a whole bunch of different functions. Let's say we choose parabolic. And with functions, usually you have to add some other data. In parabolic, it wants you to specify a starting refractive index and an ending refractive index. Let's suppose that at the end of the parabola, it's got the same modal index as the cladding. So it's going to be a gradual change in index from the core to the cladding, and I select OK. So it's a graded index of a kind. You can see that it traces out a parabola in a bunch of uniform steps. If we wanted something a little bit more accurate, we could add more steps. But the reason for the steps is that some of the algorithms of calculation algorithms are assuming constant layers only, so that this fiber would now be simulated as a a fiber with 31 layers, or 31 annuli, each one with a different refractive index in a staircase to approximate a graded index. And when we calculate with the graded index, we only have 2 modes now because the graded index fiber is holding fewer modes than the step index. There's also a tab here that shows how our fundamental mode fits into the graded index profile. You can see how they overlap. And now to demonstrate one of the main features of OptiFiber is the scanning of modes. And what's going to happen here is we're going to scan over wavelengths. We're going to scan from a wavelength of 1.2 to 1.6. We're going to do it in 30 steps. And while we change the wavelength, we're going to calculate a whole bunch of things and plot them. It's not necessary to scan over wavelength. You can also scan over other physical parameters as well. But I'm going to show you wavelength. And we click calculate, and it has now done that scan and calculation. And to see the results, we just go through the tabs. So here's the modal index of the fundamental mode at 1.2 microns optical wavelength, and the modal index becomes smaller as the wavelength becomes longer. There's also a display of group index, and group index is really the same data as group delay, but in a different units. It has also calculated dispersion as a function of wavelength. It's calculated a number of mode measures. Mode measures are different ways of classifying the size of the mode spot. There's an effective area, mean field diameter. There's Peterman 1 and 2 diameters. I have here, I copied from the OptiFiber manual what these mode measures are. Peterman 1, sometimes called near field, is calculated as a kind of moment integral, a moment of the optical intensity over with the third power. And Peterman 2, slightly different definition, slightly different meaning. And OptiFiber plots all of these as a function of optical wavelength. There's also a display of different kinds of losses that could occur in the material of the fiber. There's also a display of bending loss. It looks like bending loss is not important in this design until we get to the longer wavelengths. That's presuming that's probably because at the longer wavelengths we're approaching a cutoff, getting closer to a cutoff. And there is also an estimation of splice losses. There's confinement. There's another view that shows the picture of the mode in an optical view. And the more precise definitions of what all these things were is available from the original dialog box where we specified them. For example, material loss, there's a bunch of different material losses shown here. And what they all are comes from a dialog box associated with that. The OH absorption, for example, is from a formula. And we show what parameters we used in this formula to calculate OH loss, the kind of absorption loss. There's an estimation of infrared absorption, and we've got Rayleigh scattering by a 1/4 power law, and so on. We also had a bending loss, and how that is defined is available here. The bending loss could have been calculated by one of two algorithms. Either the default was the algorithm of Sakai and Kimura, which you can look up in the references, and the other is a reference from Snyder and Love. But in both cases, what it does is it bends the fiber according to a predetermined bending radius. Here it was 38 millimeters, and you could change that to something else if you want. It bent the fiber by this much. It applies one of these two algorithms, and that's how it got to that curve. The macro loss was calculated according to that. Let's see now. Oh, there is also a splice loss demonstrated, and how that was defined is indicated here. It's presuming that you're matching your mode to a mode of some size here, 9 microns. It assumes that there was a longitudinal separation between the fibers, here 1 millimeter. It assumes that the refractive index between the fibers was not glass, it was, in this case, it was air. It assumes a transverse offset and an angular misalignment. And by assuming all those things, it obtained the loss figures that you find in that plot. Okay, that's enough for the first half of our presentation. I'd like to take a little break now to give us a chance to look at a few of your questions, and to give Brian a chance to ask you a question. He's going to ask you a question in the form of a poll, I believe. So now over to you, Brian.
Okay, thanks, Steve. The second poll is up, and there are a couple questions that came in. Give Steve a chance to read through all those, and if you guys have any questions, please type them out now. Again, we do have another Q&A period at the end of this session, but if you get them in now, at least we can read through them and formulate a response, hopefully during the session. So it's greatly appreciated if you have any questions pending, just ask them as soon as possible. Again, we have one more day of webinars coming up tomorrow. This is the only one on OptiFiber, and tomorrow we have, I believe, OptiSystem, OptiSpice, FTTV, and another BPM. So if you're interested in any of those sessions, feel free to sign up at any time. And I think that's enough time. There's another question came in, and so if you guys still have some questions, please type them out. Looks like there's a good bunch for you now, Steve, so I'll hand it off to you and you can try to get through them.
Thank you, Brian. And we do have some questions. I have someone asking if OptiFiber is suitable for estimation of chromatic dispersion, and I would say yes, if you know the the specification of your fiber in terms of a refractive index profile, yes, it will do that nicely. Another question is about modeling of multi-core fibers. And OptiFiber, as you might have gathered so far, is going to be designing fibers that have axial symmetry. It is assumed in OptiFiber that your fiber consists of a number of concentric layers. If that's what you've got, you've only got one core. So OptiFiber will not do multi-core fibers. On the other hand, we do have another application called OptiMode, which can do modal analysis of structures like that. It's not a problem. But yeah, you'd want to use a different product. You'd want to use OptiMode for that. And the same thing applies for not circular fibers, elliptical fibers. Once again, OptiFiber is assuming cylindrical symmetry. But if you want to analyze elliptical fibers, have a look at OptiMode instead. And the same applies for photonic crystal fibers. Same story. No, it's not in the scope of OptiMode. Yes, it is. Sorry, it's not in the scope of OptiFiber. Yes, it is in the scope of OptiMode. And we have a question about writing to file data that is calculated from the various plots. And yes, you can do that. Let's have a look at calculated results. So here's all of the results that we've looked at, except this is in table form. And you can select any or all of these, and you click on Save, and it will dump all of this into a text file. So yeah, no problem getting calculated results out. All right. So what I wanted to show you now was one of OptiFiber's more clever features. This comes about as from necessity. This is a plot of dispersion, and it is showing a dispersion from various sources. There's a dispersion due to the waveguide. Optical fibers, they are waveguides, and all waveguides have dispersion, although optical fibers are very weakly guiding waveguides, and because they are very weakly guiding, there's very little waveguide dispersion. The total dispersion is shown in red, and so you can see that really most of the dispersion in an optical fiber comes from the dispersion of the materials used to make the fiber. It comes from the dispersion of glass and the various forms of glasses that we're using to make the fiber. So how does OptiFiber calculate the dispersion of materials? For that, I show a simple step index fiber. And the refractive index of the core in this fiber is 1.45. And as I mentioned before, that 1.45 only has meaning in the context of a specified wavelength. This is what the refractive index of the core was at a wavelength of 1.3 microns. Well, what does that tell us? In order to find out what this refractive index is going to be at other wavelengths, we really have to know what the material of the core is. It's not enough just to know its refractive index at one wavelength. So we have to know something about the materials. What has happened here is that OptiFiber has assumed that you have created your refractive index profile as a result of mixing different materials. And that for each material, we have a Sellmeier formula and we know how its refractive index varies with wavelength. For example, pure silica, nothing in it, it does have a definition by Sellmeier formula. There's the formula. And for pure silica, this is the values of the oscillator constants, and these are the three oscillator wavelengths. And put the wavelength in there, and you will calculate the refractive index. And what's happened, what is shown in this graph is pure silica is the host, it's the red line. This is what that Sellmeier formula calculates for the wavelength range 1.2 to 1.6. That was the range that we were looking at. Let's have a look at what's happening close to our definition wavelength. We know that the core has refractive index 1.45 at a wavelength of 1.3. So let's look and see what's happening close to that wavelength. The red line is host, which is pure silica, and the blue line is a positive dopant. This is silica that's been doped with 3.1% germanium, and it has a different Sellmeier formula. Well, same formula, but different constants. Our core has a refractive index of 1.45 at this wavelength, so it's a refractive index that is higher than pure silica, but it's lower, a little bit lower than 3.1% germanium doped silica. Our core is just a little bit less than the 3.1% doping level. So what does OptiFiber do? It interpolates. It says that based on the refractive index being 1.45 at that wavelength, it can be determined what the germanium doping level was. And it sets it to that level so that when we do a scan and we want to calculate the material refractive index over a large wavelength range, it simply interpolates to the same level all the way along, and thereby finds the refractive index of the core as a function of optical wavelength. And it goes and does the same thing for the cladding and all other layers that you might have in there. And that is how it obtains the material dispersion curve. It's just taken the average index, averaged over the fundamental mode to obtain an average kind of material refractive index, and thereby calculate the dispersion over the length. Okay, and that's just about all that I have to say about OptiFiber. Let me have another look to see if there are more questions.
While you take a look at that, I'll go ahead and launch the last poll for everybody to answer.
Righto. Thanks, Brian.
And I'll also throw down the link to the webinar page for everybody if you'd like to just click to it. Just give me a second, I'll put it in the chat window.
All right then, hearing no further questions, I'm going to close today's webinar on OptiFiber. Goodbye, and thank you for dropping in.